So my next example is a quick one, but an important one. We actually had it on the board in the previous video, but we can just look at this important series, 1 over n to the p. They call this the p series, right? They're using p for the exponent in the same way that we used the p for the exponent in the other case. The question is, for what values of p does this series converge? Super easy question to answer, because we know that this integral converges. P is greater than 1 and diverges if p is less than or equal to 1. So the p series does the same thing. Okay? Nothing really to say there, except because we already did all the work before. Isn't that nice? I told you it was important. We will use this a lot in the rest of this, in the rest of this chapter, right? Especially in the next section, 11.4, we will be comparing series to p series a lot. So it's just good to know, keep that in the back of your mind. That's what the p series does. Now we'll do one that's a little bit more interesting. N e to the minus n. Okay? So this guy, we can also think about this a little bit. What is this? I would actually expect this to converge. I'm not sure. We'll do it and see what happens. But I would expect it to converge because you've got n over e to the n. It's going to go down pretty fast. But let's see. Oops. X e to the minus x dx. Right? So I have the limit as t goes to infinity from 1 to t. And this is integration by parts. It's an easy integration by parts, right? Because u equals x and dv equals e to the minus x dx. The only thing I really have to be mindful of is my negatives, keeping my negatives together, which is the easy way to screw up these problems, right? So I've got uv minus the integral of v du. Okay. So minus and minus makes plus. So what I end up with here and going here, I've got minus x e to the minus x minus e to the minus x, evaluate from 1 to t, limit as t goes to infinity of minus t e to the minus t minus e to the minus t plus e to the minus 1. Okay, and then both of these limits actually do go to 0, right? E to the minus t is going to go to 0. Now this t e to the minus t, that is a little bit of work, right? Because this is infinity times 0. But it's not too bad, right? T e to the minus t, I write it as t over e to the t. Now it's infinity over infinity. L'Hopital's rule gives me 1 over e to the t, which then goes to 0 because it is 1 over infinity. Both of these guys go to 0. I'm left with 2 over e. Okay? So converges. Now, let me say this. This is important that we understand these things. On the WebAssign, they're just going to give you converges, diverges. And they're not going to require you to show any work or write anything down. That's not the way it's going to be on the quizzes or the tests. I expect to see why it converges or diverges. So if you're using the integral test, I expect to see your integral done completely with all the steps. If you're using some other test, you're going to have to show the steps for that test. It's not enough just to say converges and diverges. Okay, I've got another one. Both of the examples we did converge. So, well, let's see what we got now. I think I have another one which diverges. Diverge. So, next example is kind of an interesting one. For one thing, it starts from 2. And I've got 1 over n times the natural log of n. So, fine, it starts from 2, so we're going to do our integral from 2 to infinity of dx over x ln x. Doesn't look like a 2. Let's write that out in the appropriate way. This is actually an easy integral to do if you recognize it. It's a u substitution. If I let u be natural log of x, du is dx over x. So this becomes du over u, which is natural log of u. Okay? So this just ends up being the limit as t goes to infinity of natural log of u, but u is natural log of x, so I got natural log of x. Evaluate from t. See, I should have written that up there. Okay, so what I have is limit as t goes to infinity of natural log of t minus, even worse, natural log of 0. So this is actually really bad, right? Oh, except it's not 1. It's not that bad. Good. I'm like, why is it natural log of 0? That's better. That's better. I'm like, how did that happen? There. That's natural log. Okay, so this part is finite. Anyway, but this part is definitely not finite, right? Because if I take in the infinity, natural log of infinity grows without bound, right? Here's natural log. Instead of going off to infinity, it's going off to infinity. So this guy grows without bound. This integral diverges. This series diverges. And it's kind of interesting that it does that. Because natural log of n, it's like you've got n down there, and you've got natural log of n. It's getting bigger than, think of it like comparing with the p series, it's going to be bigger than 1, but it's not big enough. So that's kind of a neat one. But in the end, once you get, and it's the same thing as our usual integrals, our usual improper integrals, as soon as you get something that blows up, you're done. You don't have to worry about the rest. So I have one more example, sort of to show you. We have this nice test now, but it's just one test, and we also know some other things. So you don't necessarily have to use this test, even if it's a problem in this chapter, because one of the problems in this chapter was this, something like this. Well, I can use the integral test with this, right? But this is a rational function where the top and the bottom are both have a power of n. So if I'm going to do the integral of it, which I'm not going to bother, but you can just see it now. I'm just going to write it pretty quickly. If I have this, what do I have to do? With my rational function, I have to divide the top by the bottom so that I have something that's actually a proper fraction, blah, 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 blah. It's a little bit of a pain, okay? So you can do it. It's not that hard, but look. If I've got n in the top and n in the bottom, and I just look at the limit of that, that limit's going to 1. So it's much easier to notice that I can use a different test. I can use the test for divergence. Limit as n goes to infinity of kn. This is 1, not 0, therefore the series diverges. As we get more tests, you have more options for what you're going to use or what you could try. And a lot of times you can do these with more than one test. Some are faster than others. Some are both, sometimes more than one test. Or one test is, they're basically the same. Just some people like certain tests better than others. So you might do that. Like, I personally, I have my favorites, right? The integral test is not one of my favorites because I don't really like to do an integral if I don't have to do an integral. But some people like the integral test because it's very straightforward. You don't have to worry about anything. You just like do it and that tells you. So it's really what you like in a lot of cases. But I would certainly rather do this than necessarily do that.